6 minutes ago, in a control room in the Chilean Andes, a group of scientists watched a screen and stopped talking. Nobody moved. Nobody reached for their coffee. Because the image loading in front of them was not supposed to be possible yet. It was June 23rd, 2025, and what appeared on that screen would end up being described, within hours, as one of the most important single images in the history of astronomy. Not because it was pretty, not because it was big, but because of what was hiding inside it. 10 million galaxies in one photograph, taken by a camera the size of a small car, sitting inside a telescope named after a woman most of the public had never heard of. This is the story of the day the Vera C. Rubin Observatory opened its eye for the first time, and why astronomers are calling it the moment the sky stopped being a picture and became something else entirely. At 5:30 p.m. Central European Time, after 25 years of planning, arguing, funding fights, and construction delays, a live stream went online. At 5:30 p.m. Central European Time, after 25 years of planning, arguing, funding fights, and construction delays, a live stream went online. Scientists from the National Science Foundation and the Department of Energy sat in front of cameras to reveal something the public had waited 2.5 decades to see. Not a rendering, not a simulation. A real photograph of real space, taken days earlier using only about 10 hours of test observations. And the first image they showed the world was of the Virgo cluster, a collection of galaxies roughly 55 million light-years from Earth. Here is where it stops sounding like a normal astronomy headline. That single image was built from over 1,100 overlapping exposures. It contained 3 trillion pixels, and buried inside all of that resolution were an estimated 10 million galaxies. Not stars, not planets, galaxies. Each one a cluster of billions of suns, each one older than human civilization, by a margin so large the number stops meaning anything. And according to scientists at NOILAB, that jaw-dropping number was only about 0.05%, 1/20th of 1%, of what this same observatory is expected to capture over its full 10-year mission. Sit with that for a second. If 10 million galaxies in a single frame is the appetizer, the full meal is expected to be roughly 20 billion galaxies. We are not looking at a big discovery. We are looking at the smallest possible sample of something almost too large to comprehend. But the galaxy count is not even the detail that made scientists lean forward in their chairs. It's what was moving inside the frame. Because tucked into the corner of that first release was a second image, one that looked almost unremarkable at first glance. 2 glowing clouds of gas and dust, called the Trifid and Lagoon nebulae, stitched together from 678 individual exposures. Stellar nurseries. Regions where new stars are actively being born right now, light years away, captured in a level of detail no ground-based telescope had produced before. And according to Rubin's own project scientists, that image represented barely 2% of the full field of view a single exposure from this camera can capture. 2%. That was the preview. The full picture was still coming. Here's the part that should genuinely make you pause. This wasn't even the observatory's real mission starting. This was 10 hours of test data, a warm-up, a stretch before the real race began. And in those 10 hours, buried quietly in the data almost as an afterthought, Rubin had already found something else. 2,104 previously undetected asteroids in our own solar system, including 7 near-Earth objects. 2,000 new asteroids, from 10 hours of pointing a camera at the sky, before the mission had technically even begun. To understand why that number is so unsettling, you need to understand what came before it. Every telescope in human history operated the same basic way. Point, focus, capture, done. One subject, one shot, one frozen moment. Hubble gave us breathtaking detail. James Webb gave us the infrared afterglow of the early universe. Hubble gave us breathtaking detail. James Webb gave us the infrared afterglow of the early universe. But neither one was built to return, again and again, to the same patch of sky and ask a simple, dangerous question. What changed since last time? Rubin was built entirely around that question. And that single design decision is why scientists describe it in a very specific way. Rubin does not just photograph the universe. It gives the sky a memory. And a universe with memory behaves very differently than a universe frozen in a photograph. It starts confessing things. A missing asteroid becomes a clue. A faint smudge becomes a hidden dwarf galaxy nobody catalogued. A blinking dot becomes evidence of something that used to be there and now is not. So if 10 hours of test data quietly produce 2,000 new asteroids and 10 million galaxies, the obvious question becomes unavoidable. What happens when this machine is actually turned on? Before we get there, I want you to understand exactly how this camera does what it does, because the engineering behind it is almost as wild as what it found. The instrument responsible for all of this is called LSST-CAM, the Legacy Survey of Space and Time Camera. It is, without exaggeration, the largest digital camera ever constructed by human beings, roughly the size of a small car, built to sit inside an 8.4-meter telescope on a mountain called Cerro Pachon, 5,200 feet above sea level, specifically chosen because the air there is dry, dark, and still. A single exposure from this camera covers an area of sky equivalent to roughly 45 full moons at once. Not a tight, zoomed-in shot of one object. A wide, staggering gulp of the entire sky in one frame. And once the real 10-year survey begins, the camera is designed to take a new photograph roughly every 30 seconds. All night, every clear night, for a decade. Every 3 to 4 nights, it will have photographed the entire visible southern sky. Not one galaxy, not one cluster. The entire sky. Then it compares the new image to the last one. If a single point of light has moved, brightened, dimmed, appeared, or vanished, an automated system flags it instantly, without a human ever having to notice first. Scientists have projected that once this system reaches full operating speed, it will generate somewhere around 7 million alerts a night. 7 million. Every single night for 10 years. That is not a photograph anymore. That is a live nervous system wired directly into the universe. And the first images released on June 23rd were the clearest possible proof that this system already works exactly as designed, using a fraction of its actual power. Here's the detail that made a lot of scientists stop scrolling through the press release and start rereading it. One of the lead engineers on the project, physicist Vera Rubin, described the first Virgo cluster image as something closer to a demonstration than a final product. A way of proving the machine could do in 10 hours what would have taken older instruments weeks or months to assemble. And Rubin's deputy director, Zeljko Ivazic, said something that quietly reframed the entire release. He pointed out that the striking spiral galaxy image the public saw earlier in the day, the one people were already sharing everywhere online, represented only about 2% of what was actually captured in that single frame. 2%. The image that broke the internet that day was a rounding error compared to the full data sitting behind it. So what was Rubin actually built to find, once you strip away the demonstration and get to the real mission? The answer takes us back to the woman this observatory is named after, and why her name on the side of this telescope is not a courtesy title. It's the entire point of the machine. Vera Rubin was an American astronomer working in the 1970s who noticed something that did not add up. She studied how fast galaxies rotate and found that stars on the outer edges of spiral galaxies were moving far too quickly. Based on the visible matter inside those galaxies, stars out at the edges should have been flung outward into space entirely. They weren't. Something invisible had to be holding them in place, providing gravity that no telescope could see or photograph directly. That invisible substance is what we now call dark matter. And Rubin's observations became some of the strongest evidence in the history of physics that it actually exists. She never lived to see a telescope carry her name into operation. But this entire 10-year mission is, in a very real sense, the continuation of the exact question she first asked half a century ago. What is actually holding the universe together? Here's how the observatory plans to answer it. As light travels across the expanding universe toward Earth, it stretches, shifting toward the red end of the spectrum. The more stretched that light is, the farther away its source. By measuring this shift, called redshift, across billions of galaxies, Rubin can effectively map how mass, including invisible mass, is distributed across distances that are almost impossible to picture. Scientists confirmed that even in Rubin's earliest preview data, This technique was already performing at least as well as observatories that took years to reach full capability. And once the full 10-year survey wraps up, Rubin is expected to measure the redshift of roughly 4 billion galaxies out of the 20 billion it will ultimately observe. 4 billion galaxies, mapped for distance and position, effectively building a chart of where the invisible skeleton of the universe actually sits. But dark matter is only half of the mystery this telescope was built to chase. The other half is dark energy, the still unexplained force that appears to be causing the expansion of the universe to accelerate rather than slow down. Scientists still do not know what dark energy actually is, where it comes from, or whether it will keep behaving the same way forever. And the tool they're using to test it comes from something that exploded inside that first image and nobody outside the astronomy world noticed. Type 1, a supernovae. A very specific kind of exploding star that astronomers use as a cosmic measuring stick, because they all explode with almost exactly the same brightness, which means the dimmer one looks, the farther away it is. In the late 1990s, two research teams studied fewer than 100 of these exploding stars and made one of the most important discoveries in modern physics, that the expansion of the universe is accelerating. That discovery won a Nobel Prize. It rewrote the ending of the universe as scientists understood it. They did that with fewer than 100 data points. Once Rubin's full survey is running at capacity, scientists expect to find around 250,000 of these exploding stars every single year. Not 100 over a decade, 250,000 annually. Researchers are hoping this flood of new data can finally help resolve something called the Hubble tension, a long-standing disagreement in physics where the modern universe appears to be expanding faster than early universe measurements predicted it should be. If Rubin's data settles that disagreement, it will resolve one of the biggest open arguments in cosmology, using math nobody could attempt with the tools that existed before this telescope switched on. Now step back and look at the full picture of that one day again. On June 23rd, 2025, using 10 hours of test data and a camera the size of a car, this observatory produced a single image containing 10 million galaxies. Hidden in the same release were two glowing stellar nurseries captured in unprecedented detail, and over 2,000 previously unknown asteroids discovered almost as a side effect. And every single person watching that live stream understood, in real time, that they were looking at roughly 2% of what the camera was actually capable of capturing in one frame. We spent thousands of years looking up at a sky that seemed permanent, fixed stars, frozen constellations, a universe so vast and so slow that a human lifetime felt too short to ever notice it move. The first images from the Vera C. Rubin Observatory proved, in a single afternoon, that this was never true. The sky was never still. We simply never had a machine capable of remembering what it looked like yesterday, so it could notice what changed today. Now we do. And this was only the introduction. So here's the real question, and I want you to actually sit with it before you go. This was 10 hours of test data, a stretch before the real race even started. If 10 hours produced 10 million galaxies, 2 exploding stellar nurseries, and 2,000 new asteroids, what happens when this same machine runs at full power for a full year? What happens at year 5? What happens at year 10? When the 10 million galaxies in that first image turn out to be the smallest fraction of 20 billion. How much of the sky has always been changing right above us, quietly, while we assumed it was standing still? If this kind of story pulls you in, the way a single photograph can quietly rewrite what we thought we understood about the universe, make sure you're subscribed, because this observatory has 10 years left on its clock, and what it already found in its first 10 hours is only the beginning. Drop a comment and tell me which detail from this video actually stopped you. The 10 million galaxies in one frame, the 2,000 asteroids found almost by accident, or the fact that the image everyone shared online was only 2% of what the camera actually captured. And if you want to go deeper into what happens once this same telescope turns its full power toward hunting dark matter and dark energy, there's another video linked right now that you need to watch next.